Hi everyone. Today we are going to discuss on the topic control design and simulation model. Generally, the LabVIEW control design and simulation model helps us to analyze the open loop model behavior, design closed loop controllers, simulate online and offline systems, and conduct physical implementations. Okay, within this, we what are the things that we can done with control design and simulation? We can construct plant and control models with the help of transfer functions, state space, or zero pole gain. From this, analyze system performance with tools such as step response, pole zero maps, and body plots. We can simulate linear and nonlinear discrete systems with wide option of solvers. Deploy dynamic systems to real-time hardware using built-in functions and real-time modules. Well, if we keep elaborating this, we can create models from the first principles using transfer function, state space, or zero pole gain representation. With time and frequency analysis tools, we can obtain the time step response or body plot, or we can analyze the open or closed loop behavior of the transfer function or state space models that we have designed using built-in tools for both multi input multi output or single input single output systems. We can verify the linearity and non-linearity of the system dynamics. Also, LabVIEW has control design simulation usability with other NI software. For example, we can use LabVIEW system identification toolkit to find empirical models from real-time plant stimulus response information, and we can use state chart module for event based control design or event driven simulations. And also we can deploy dynamic system to real-time hardware targets with the help of LabVIEW real-time model or rapid prototyping done. This is the control system model. We have a control system. The main parts of the control system is your reference inputs, controller, actuators, physical plant, and sensors. So how does the control system works? Generally, first we are giving the reference input that we call it as set point. So the next one is the error detector, and the next one is controller, actuator, physical system like the process plants and sensors. What happens in this control system is, first we are giving the set point input. First it will senses the output from using the sensors, and it will compare with the reference input. The difference between the sensor output and as well as the reference input is take given by the taken by the error detector, and it is given to the controllers. So the based on the controller settings and the input from the error detector, the controller takes some actions that is given to the actuators. That actuator is make the physical system to move towards the reference input. If there is any deviation in this error detector, it will adjust the plant operations towards the reference input. The next one we are going to discuss is model based control design. In the model based control design, we can create control applications, the LabVIEW system identification toolkits. The first one is plant modeling and analysis. Here we are going to acquire the data from the plants, because in control system models we have seen there is a plant where we can acquire the data, and the acquire the data using sensors, and the data is compared with error detector with reference input, and it is given to controllers. In that case, there is a need for custom control algorithm for the controllers. When designing these control systems, control engineers used the model approach. This consists of using mathematical models to represent plants and controllers. So, the model based control system can be broken down into four steps. The first one is plant modeling and analysis, control design, simulations, and prototyping. In plant modeling and analysis, we are acquiring the input output data from the plant, and we can identify the plant structures and coefficients. In control system design, first we are creating the open loop characteristics of the plant, and we are identifying the controllers, structures, coefficient gain. From that open loop, we are converting that into the closed loop so that the output can be compared with the input, and we are started tracking the plant output towards the reference input. Then simulation, it will simulate the offline controllers and linear plant models. Also, we can simulate with non-linear as well as non-linear plant model. Then prototyping, so the prototyping is nothing but we are based on the transfer function, open loop and closed loop transfer function, we are creating the control algorithm which will control the real world dynamics. The next one is LabVIEW control and design tools. So the LabVIEW control and design tools are mainly used for control applications. We have three types of control design tools. The first one is LabVIEW system identification toolkit. The second one is LabVIEW control design toolkit. The third one is LabVIEW simulation toolkits. So everything is mainly used to perform the control applications, because we have different types of controls. Plant systems are the control systems, so based on the application we have to select our control design tools. So using the LabVIEW system identification toolkit, the design engineer will begin the control design process by creating a model of the plant. This begins with acquiring the stimulus response data from the plant using the standard data acquisition hardware, and then selecting a plant structure that fits this data. From there, we'll find the right coefficients for the plant model that accurately represents the plant. Next, after system identification, we have to move on to the control system design. Here, the control design toolkit will develop a controller for the plant. First, the engineer will analyze the open loop characteristics of the plant and then select the basic control structure to control this plant. From this information, they will determine the right coefficients for this controller. Finally, the engineer will connect the controller with the plant and analyze the closed loop characteristics of the controlled plant. Then LabVIEW simulation toolkit. Here, the LabVIEW simulation toolkit enables the simulation of the controller with the linear plant model. Next, we can extend the simulation to the nonlinear plant model to accommodate for nonlinear operating conditions in the real world. After performing the system identification, control design as well as simulation, we can create a prototype in the real-time order and we can test it against the real-world dynamics. The next one is PID controller toolkits. Here the control design. We keep on telling we have to predict the open loop system and we have to apply the gain and we have to create an algorithm which shoots for the plant. So generally the most commonly used control algorithm is PID controller, the proportional integral derivative controller. Here the proportional controller will vary the actuator based on the proportional to that error. The integral control integral of the error, and the derivative controller the derivative of the error. So based with this, the proportional integral derivative algorithm is most commonly used one for performing the control system applications. So we have a LabVIEW PID toolkit that can be used to solve this so many applications. but the PID controller is sometimes insufficient to apply for specific application, because in some cases we have more complex higher order controller is required, or the controller must compensate for nonlinear behavior in the plant. So the PID controller we cannot employ because it is incapable of achieving the required performance, because the control algorithm is single input and single output control. If you want to handle complex multi input multi output systems, we cannot employ PID controllers. But the PID controllers can be used for, it is effectively used for single input and single output control applications. The PID control systems can be applied to multi-input, multi-output systems, because it will mainly keep tracking of a single parameters. It is not employed for multiple parameters that is to be measured at the same time. For that, we have go with other options like data logging and supervisory controls. The National Instruments LabVIEW data logging and supervisory control model is the best way to interactively develop your high channel count and distributed monitoring and control systems. The LabVIEW data logging and supervisory control model provides built-in utilities for data logging and alarm management, as well as real-time historical trending. Whether you are collecting data from the National Instruments data acquisition products, LabVIEW real-time targets, compact field point or compact Rio models, or programmable logic controllers, we can quickly configure the input output whatever we want with LabVIEW DSE models to automatically acquire the data. Also, the NI LabVIEW data logging and supervisory control model extends the LabVIEW application development environment to interactively configure and manage alarms and events, efficiently log data to a distributed historical database, view real-time and historical data, set application security, and easily network LabVIEW real-time targets and other OPC devices to create one complete system. Whether we need to build a full-scale industrial automation and control system, configure thousands of channels in a data logging application, or just monitor a few I/O points for historical collection, the LabVIEW DSC model provides tool to do that. And also, there is so many applications we can develop with LabVIEW. So these are some of the applications where we it is found in industrial environment. For example, consider an oil refinery process that continuously manufacture and produce oil. The control system used for processing may consist of programmable logic controllers executing PID algorithm, or distribute control systems for a large process. In this case, the control system is used to manufacture a product. A control system can also be part of an end product being manufactured. This has been seen primarily in automotive and aerospace industries with electronic control unit and flight control systems. However, the control systems are now finding their way into the other end products such as precision motor controllers for computer hard drives, while goods like washing machines, etc. So, the control systems with LabVIEW be can move forward for all industrial applications, everything. Hope this video will give you more information about control system modules, how then control system design, as well as simulation with LabVIEW. Thank you.